Okay, hello everyone, good afternoon. Our project is about a comparison of graph neural networks for node classification. Here, there are 4 members in our group. Here we roughly show our contribution in this project. Our presentation is following this outline. First, we'll talk about the introduction, later related work, methodology, and last but not least, experiments. So my name is Xu Yan. Now I'll start to talk about some background knowledge of our project. A graph consists of entity nodes and the relationship between the entities. It is a special but common data structure in practice. The graph data from science, nature, technology is more similar than one would expect. In other words, graph could be considered as a universal language for describing complex data across different domains. When we try to leverage the data for machine learning or say deep learning downstream tasks, the whole pipeline is shown in the figure, where the feature extraction is one of the most important steps. However, it's hard to encode the graph data. Image data has a fixed 2D dimension, which is suitable for being encoded with convolutional neural networks. Well, for text and speech signals, they have linear one-dimension structure by nature, which is suitable for being encoded by RNN-based or transformer-based models. However, the graphs, different from the aforementioned 2 types, have arbitrary size and much more complex structures, which makes them hard to be encoded with those models. Similar to CNN and RNN, graph neural networks work as a feature extractor, especially for graph data, and contribute to many graph-related tasks. Up to now, there are a bunch of novel GNN models have been proposed and achieved great progress in node classification, graph classification, link prediction, this kind of graph-related task. In this project, we mainly focus on the node classification task, which is to predict the label of a given node in the graph. For an interview of our project, we conduct a comparison between these GNN models with different number of layers. The models are evaluated on 3 commonly used graph datasets, Cora, Setseer, and PubMed. A clear insight about the key component and structures is included. A case study to show how GNN models work is also reported here. Here, we're gonna talk about the related work. Oversmoothing issue is an important problem in GNN models. Previous work showed that doing too much aggregation on the entire graph will reduce all node features at a fixed point and call this phenomenon as oversmoothing. There's a new published paper in KDD 2020 proposed a model called ALA-GCN, measures neighborhood entropy and center neighbor similarity in the information propagation. So the more CNS and NE is obtained, the less information propagation should be conducted. This is to avoid the model from doing too much aggregation in the information propagation, and then we can alleviate the over-smoothing problem.
Okay, hi, I'm Xiaozhe. Next, I would like to introduce the methodology of our project together with Junjie. In this project, we mainly focus on 5 kinds of graph neural networks. Now, I'd like to introduce the first one, convolutional neural network. Graph convolutional neural network considers the problem of classified nodes in graph where only a portion of nodes have label information. This problem can be modeled as a graphic-based semi-supervised machine learning problem. The key idea of GCN is to process a graph data by first-order approximation of localized spectral filters. Okay, next slide. Here is a structure of graph neural network, where C is the input channel and F is a feature map in the output layer, and labels are denoted by Y. The graph structure is shared over layers. Consider n nodes with features. The layer-wise propagation rule can be formulated as the formula below. A is an adjacent matrix of n nodes, and I is an identity matrix. D is a degree matrix of A, which can be computed from A. H is a hidden feature of each layer. Note that the formulation D multiply A and multiply D before the H can be pre-calculated. So the graph convolutional neural network can be considered as a fully connected network with neighborhood aggregation components. Although GCN is a powerful tool to handle transductive graphic tasks, but its poor performance on inductive tasks. Also, GCN is difficult to allocate different importance to neighborhood. To this end, attention mechanism is proposed to solve graph problem in 2017, which is graph attention networks. Attention mechanism is widely used in natural language processing and computer vision applications. Left picture shows attention mechanism employed by a model. Consider two nodes I and J. H is a feature of corresponding nodes. W is a shared weight matrix which projects features to some space. By applying attention function, the network can get the importance of node J's feature to node I. The right picture shows the multi-head attention by node 1 on its neighborhood. With multi-head attention, the network can learn multiple features in different subspace. This slide shows the formula of attention mechanism and hidden features for each node. To utilize such mechanism in graphic data, naturally, there are two kinds of attention. One is to calculate attention for every node in network, but the computation cost will be expensive and the detailed graph structure information could be discarded. GAT choose masked attention, which only considers the neighborhood of node I. The attention mechanism only considers interested node feature information, so the model is independent of graphic structure, which can handle inductive tasks, which is a key feature of GAN. Okay, next slides.
Hi, I'm Junjie, and I'm going to talk about the following three kinds of graph neural networks. So the first one is GraphSAGE. So as we can see, previous graph neural networks were performing well on fixed graphs. However, they could not adapt to unseen nodes easily. Also, there might exist some easy ways to convert current methods to an inductive setting. Although this is doable, it is very costly. Next page. So in 2017, GraphSAGE is introduced to solve this problem. As we can see, instead, when a new node comes in, instead of updating all the node embedding again, using the aggregation function in GraphSAGE, we can easily compute the new node embedding for node A using this learnable aggregation function with the following formula. So here we can see that we can update the node embedding easily using the learned aggregation function. Next page. And also in the GraphSAGE paper, they provide three types of aggregators. The first one is the mean aggregator. The second one is the pool aggregator, and the last one is they use the LSTM as the aggregation function. Next. And also in 2019, another strong model called Isomorphism Network was introduced. So here we will first talk about the WL test. WL test will first aggregate the labels of nodes and their neighbors, then hashes these aggregated labels into unique new labels. And at last, this test will decide two graphs to be non-isomorphic isomorphic if at some iteration, the multi-sets of labels between the two graphs differ. And this paper also proves that GNNs are at most as powerful as the WL test in distinguished graph structures. Next. So here we first define a unified notation of GNN's aggregation schemes like this. And phi and f are two learnable functions which operates over multi-sets, are injective, and graph level readouts are also injective. The GNN is as powerful as the WL test. Okay, next. So here we can see the aggregation scheme of the GIN model. The composition of functions f and phi is modeled by multi-layer perceptrons, and also there are a series of maximally powerful GNNs, and GIN is the simplest one, yet keeping the extensive capability. So GIN is proposed here. Next. And finally, in 2020, another model called Deep Adaptive Graph Neural Network was introduced. Because deep GNN models always suffer from the oversmoothing issue, and since when GNN model goes deeper, the node information is propagated to the nodes far from it, which means the receptive field is large. So to solve this problem, DAGNN was proposed. Next. So here we can see how DAGNN is defined through these 6 formulas. We will not go to the details of them, but here are 2 points that need to be clarified. The first one is DAGNN proposed trainable projection vector S as a retainment measure, and secondly, the projection vector is applied to adaptively balance the weight of the representations obtained from different propagation layers instead. Okay.
Hi, my name is Ke Haowen, and I will introduce you the experiments part. So first, we will introduce you the dataset statistic and hyperparameters. In table 1, we use 3 publication datasets, Coral, CiteSeer, and PubMed. The size of Coral and CiteSeer are comparable. PubMed is a much larger graph. Coral and CiteSeer has 3,000 nodes and 5,000 edges. PubMed has 20,000 nodes and 45 edges. The class number range from 7 to 3. In hyperparameters, all models are validated under the layer number set to 3, 5, and 7. The hidden dimension of most models are set to 64, except for GraphSAGE. The hidden dimension of GraphSAGE is set to 128. Given the motivation of DAGNN is to develop deeper model, DAGNN is also tested with the layer number set to 10, 15, 30, and 100. 80% of nodes are taken as training set. 10% of nodes are taken as development set, while the remaining 10% of nodes are taken as test set. Next slide. Here comes the overall accuracy on the 3 public datasets. Although TCN is a vanilla GNN, achieves competitive performance among 3 datasets. Even the structure is simple, it still achieves 86.4 accuracy in PubMed, outperform GAT and GraphSAGE. GAT built on top of attention mechanism is likely to overfit the small datasets. In Coral, when the layer number is set to 7, GAT cannot converge. The performance drop of GAT is obvious. However, GIN is less vulnerable to overfit, and with increasing layer number, GIN improves its accuracy. In Coral, when the layer number is set to 5, GIN achieves the state-of-the-art results. As for DAGNN, this work is to develop deep GNN. Even though we set a layer number to 3, 5, and 7, it still achieves great performances. It is the state-of-the-art model on StatSeer and PubMed. Next slide. Here comes a visualization of prediction on CRUD Club. GCN and GraphSAGE could classify node 0 and 33 correctly with 10th epoch and 20th epoch. And for GraphSAGE, the node 0 and the node 33 are actually very far away. So the result is pretty good. GIN misclassified node 33 in 10th epoch. Even in 20th epoch, it correctly classifies the node 0 and 33. Those two nodes are very close. So that is because GIN takes more time to converge. In CRUD Club, it takes 40 to 50 epochs to be optimized for GIN. Next one. Then we analyze the performance of DAGN with deeper network structure. Layer number of normal GN is set to 3 to 10. Only DAGN could be this deep, that is 100 layers. We test the performance drop with layer number increase. DAGN with 5 to 15 layers achieves best performances. The deeper DAGN is, the worse performance it achieves. But the performance drop is not very substantial, so it do elevate the over-smoothing issue and still achieve great performance when the model is very deep. And thank you, that will be all.